Welcome to Astro Dreams, a place where the universe slows down and your mind can wander through stars, galaxies, and cosmic mysteries. If you love space, relaxing facts, and dreamy journeys beyond Earth, you're in the right place. Don't forget to subscribe and join us on this peaceful adventure through the cosmos. Let's begin. A black hole can bend light so strongly that even the path of brightness curves around it, continuing on a different direction without any sound or disturbance. You can settle into this quiet rhythm, where each idea arrives softly and then fades with no need to remember or hold on. The pace remains even, and nothing requires attention. These facts move like distant stars, present but not demanding, forming a calm background for rest. Black holes form when very large stars reach the end of their life cycle and collapse inward under their own gravity. This collapse becomes so dense that a region forms where gravity dominates everything nearby. The boundary around a black hole is called the event horizon. It marks the point where escape is no longer possible, even for light, and it exists as a smooth, invisible surface in space. Black holes do not pull objects in like a vacuum cleaner. From far away, they behave like any other object with the same mass, following the same gravitational rules as stars or planets. If the sun were replaced by a black hole of equal mass, Earth would continue orbiting in the same way, moving along its path without sudden change, only without sunlight. The center of a black hole is often described as a singularity, a point where density becomes extremely high and current physics cannot fully describe the conditions. Time behaves differently near a black hole. As one moves closer, time slows down relative to observers far away, creating a gradual difference in the flow of moments. This effect, known as gravitational time dilation, happens because strong gravity influences the structure of space-time itself, gently stretching the passage of time. Black holes can vary in size. Some are only a few times more massive than the sun, while others, called supermassive black holes, contain millions or billions of times more mass. At the center of most galaxies, including the Milky Way, there is a supermassive black hole quietly influencing the motion of stars around it. The supermassive black hole in the Milky Way is known as Sagittarius A*, and it remains stable, surrounded by stars that orbit in slow, predictable paths. Matter falling toward a black hole often forms an accretion disk, a flat, rotating structure of gas and dust that gradually spirals inward. As material in the accretion disk moves closer, it heats up due to friction and gravitational forces, sometimes becoming one of the brightest sources of energy in the universe. Despite this brightness, the black hole itself remains unseen, defined only by its influence on the space around it. Some black holes emit jets of energy from their poles, extending far into space. These jets are formed by complex interactions between magnetic fields and fast-moving matter. The shape of a black hole is not a hole in the usual sense, but a region where space-time curves inward, forming a deep gravitational well. Light passing near a black hole can be bent into arcs or rings, creating visual effects known as gravitational lensing. This bending allows distant objects to appear distorted or duplicated as their light travels along curved paths before reaching an observer. Black holes do not last forever. Over very long periods, they can slowly lose energy through a process called Hawking radiation. This radiation is extremely weak for large black holes, making the process take far longer than the current age of the universe. Smaller black holes would lose mass more quickly, gradually shrinking over time until they eventually fade away. The temperature of a black hole is related to its size. Larger black holes are colder, while smaller ones are warmer, though still very faint. Black holes can merge with one another, combining their mass and forming a larger black hole. These events release energy in the form of gravitational waves. Gravitational waves move through space as gentle ripples, stretching and compressing distances slightly as they pass. These waves were first directly detected in 2015 confirming predictions made long ago about how massive objects interact. The region around a black hole can be calm at a distance, with stars orbiting slowly, creating a stable environment despite the presence of strong gravity. Objects falling toward a black hole would experience tidal forces, where gravity pulls more strongly on one side than the other. This stretching effect is sometimes described as spaghettification, where an object becomes elongated as it moves closer to the event horizon. For very large black holes, these tidal forces at the event horizon can be relatively gentle, allowing an object to cross without immediate disruption. Inside the event horizon, all paths lead inward, and movement toward the center becomes unavoidable, guided by the structure of space-time itself. Black holes can influence the formation and evolution of galaxies by regulating the flow of gas and energy in their surroundings. Some galaxies appear quiet, with their central black holes not actively consuming material, while others show bright activity due to active accretion. The size of a black hole's event horizon depends on its mass. This boundary is often described by the Schwarzschild radius. The Schwarzschild radius grows in direct proportion to the mass, creating a simple relationship between size and gravitational strength. Black holes are described by only a few properties: mass, spin, and electric charge, making them surprisingly simple despite their complexity. Spin affects how space-time twists around a black hole, creating a region called the ergosphere where objects cannot remain still. In the ergosphere, space itself is dragged along by rotation, a phenomenon known as frame dragging. Energy can, in theory, be extracted from this region through specific processes involving motion and rotation. Black holes are silent. They do not produce sound, as sound requires a medium like air, and space remains mostly empty. Their presence is known through motion, light, and the gentle influence they have on nearby objects. The study of black holes combines gravity, quantum mechanics, and relativity, bringing together different areas of physics into one quiet subject. As each idea settles, the rhythm continues unchanged, with no need to follow closely, allowing the mind to drift while the steady flow remains. Black holes can exist in different environments, from isolated regions of space to dense clusters of stars where interactions occur slowly over long periods. In a binary system, a black hole may orbit with a companion star, gently pulling matter from the star's outer layers, forming a steady stream of gas that moves inward. This gas gradually spirals closer, forming a thin disk that rotates smoothly, with each layer moving at slightly different speeds. Friction within this disk causes the material to heat, sometimes glowing softly in wavelengths that can be observed from far away. Even with this activity, the black hole itself remains a quiet center, defined only by the boundary that surrounds it. The idea of escape velocity helps describe black holes. At the event horizon, the escape velocity equals the speed of light, making departure no longer possible. Far from the black hole, the escape velocity decreases, allowing objects to move freely if they maintain sufficient speed. The gravitational pull of a black hole follows the same inverse square law as other massive objects, becoming weaker with distance. Because of this, black holes do not roam through space, consuming everything around them. Their influence remains limited by distance and mass. The formation of a black hole often begins with a supernova, where a massive star sheds its outer layers, leaving behind a dense core. If this core is heavy enough, gravity overcomes all other forces, leading to collapse and the creation of an event horizon. Some black holes may form directly from the collapse of large clouds of gas in the early universe, without first becoming stars. These early black holes could have served as seeds for the growth of supermassive black holes found in galaxies today. Over time, black holes can grow by merging with others or by slowly gathering surrounding matter. The process of growth is steady and gradual, unfolding over millions or billions of years without sudden change. Black holes do not emit light from within, but the space around them can be filled with radiation due to energetic processes. The light observed near black holes often comes from heated gas, not from the black hole itself. In images captured by telescopes, black holes appear as dark regions surrounded by glowing rings of material. This appearance comes from the bending of light and the motion of matter near the event horizon. The first image of a black hole was captured in 2019, showing a bright ring around a dark center, consistent with theoretical predictions. This image represented a combination of data from multiple telescopes working together across the Earth. The shadow seen in such images corresponds to the event horizon in the region where light cannot escape. There exists a region called the innermost stable circular orbit, where objects can maintain a steady path without falling inward. Inside this region, stable orbits are no longer possible, and matter begins to spiral toward the center. The size of this orbit depends on the mass and spin of the black hole. Faster spinning black holes allow stable orbits to exist closer to the event horizon. The rotation of a black hole can also affect the shape of the event horizon, making it slightly flattened at the poles. This rotation creates a dynamic structure where space-time itself is gently twisted. Black holes are often surrounded by halos of high-energy particles, forming a region of activity that extends beyond the disk. These particles can interact with magnetic fields, producing radiation across different wavelengths. The study of these emissions helps scientists understand the conditions near black holes. Black holes can exist quietly for long periods, with little material falling into them, making them difficult to detect. In such cases, their presence is inferred through the motion of nearby stars or gas clouds. The calm nature of these systems allows for steady observation over time. Some black holes may wander through space after being ejected from their original locations due to gravitational interactions. These isolated black holes would move silently through the galaxy, largely unnoticed. Detecting them requires observing subtle gravitational effects on nearby objects. Black holes can also act as gravitational lenses, magnifying distant stars and galaxies behind them. This effect can briefly brighten background objects as the black hole passes in front of them. Such events are rare, but provide valuable information about the distribution of black holes. The universe contains many black holes, each existing quietly within its own region of space. Black holes can have powerful magnetic fields generated by the motion of charged particles in the accretion disk. These magnetic fields can guide the formation of jets that extend far beyond the galaxy itself. Jets can travel at speeds close to the speed of light, carrying energy across vast distances in space. Despite their scale, these processes remain steady and continuous, unfolding without sudden shifts. Black holes can influence star formation in their galaxies by heating gas and limiting how it condenses. In some cases, this influence slows the formation of new stars, creating a balance within the galaxy. The interaction between black holes and galaxies forms a quiet relationship that evolves over long periods. Black holes also play a role in shaping the motion of stars near the centers of galaxies. Stars close to a supermassive black hole can orbit at very high speeds, following predictable paths shaped by gravity. These orbits can be measured to determine the mass of the black hole at the center. Astronomers use these observations to study the properties of black holes without directly seeing them. Black holes can also bend the path of radio waves, X-rays, and other forms of electromagnetic radiation. This bending allows scientists to observe effects that reveal the presence of strong gravity. The region just outside the event horizon can be described using general relativity, where space-time curves smoothly. This curvature determines how objects move, replacing the idea of force with the geometry of space and time. Objects in orbit around a black hole follow paths called geodesics, which represent the natural motion through curved spacetime. These paths are smooth and continuous, shaped only by the structure of the gravitational field. The closer an object gets to the black hole, the more pronounced the curvature becomes. This results in orbits that can be tightly bound, looping close to the event horizon. Black holes can also affect the timing of signals, causing delays as light passes through curved spacetime. This delay is subtle but measurable, providing another way to study gravitational effects. The environment around a black hole can contain gas clouds that move slowly, influenced by gravity over long timescales. These clouds may drift closer or remain in orbit, depending on their speed and position. The temperature of gas near a black hole can vary widely, from cold outer regions to very hot inner areas. This variation creates layers within the accretion disk, each with its own properties and motion. The disk itself can remain stable for long periods, maintaining a steady flow of material inward. Small changes in the disk can occur as new material arrives, but these changes tend to be gradual. Black holes can also be surrounded by a region of faint radiation known as a corona, extending above and below the disk. This corona consists of energetic particles that interact with light, scattering it in different directions. The structure of the corona is not fully understood, but it remains a consistent feature in many systems. Black holes do not have a surface in the traditional sense, only a boundary defined by the event horizon. Crossing this boundary does not involve a physical barrier, but rather a change in the possible paths through space-time. From an outside perspective, objects approaching the event horizon appear to slow down and fade. This effect is caused by time dilation and the shifting of light to longer wavelengths. The light becomes redder and dimmer until it is no longer visible, blending into the darkness. For the object itself, however, the crossing would occur without noticing a specific moment, continuing inward smoothly. Their presence adds to the structure and balance of the cosmos, influencing motion without constant activity. As these ideas continue, they move at the same gentle pace, with each fact arriving and then fading into the background. The steady rhythm remains unchanged, allowing the mind to drift comfortably while the quiet nature of black holes continues. Black holes can be described using simple equations that relate mass, distance, and curvature, forming a quiet mathematical framework that remains consistent across different environments. The mass of a black hole determines how strongly it curves space-time, and this curvature defines the motion of nearby objects. As distance increases, the curvature becomes less noticeable, blending smoothly into the wider structure of space. The idea of space-time combines space and time into a single fabric, where gravity is expressed as a gentle bending rather than a direct pull. Objects moving through this fabric follow paths that require no effort, guided naturally by the shape of their surroundings. Black holes represent regions where this curvature becomes very deep, forming a kind of slope that leads inward without interruption. The deeper the slope, the more pronounced the path toward the center becomes, though this change happens gradually. Light traveling near a black hole continues to move at its constant speed, but its direction shifts as space-time curves around it. This results in light taking longer paths, sometimes looping partially around the black hole before continuing outward. The bending of light can create rings known as Einstein rings, where a distant object appears as a circle of light. These rings are formed when the alignment between observer, black hole, and distant object is nearly perfect. Even when the alignment is not exact, the light can still be stretched into arcs or multiple images. The difference between these perspectives reflects the way time behaves differently in strong gravity. Black holes can be described as having entropy, a measure related to the amount of information they contain. This entropy is proportional to the area of the event horizon, rather than the volume inside. This idea connects black holes to thermodynamics, linking gravity with the behavior of heat and energy. The temperature associated with a black hole is extremely low for large ones, making their radiation difficult to detect. Over immense periods, this slow radiation leads to a gradual loss of mass. As mass decreases, the temperature rises slightly, increasing the rate of radiation in a steady progression. This process remains theoretical for most black holes, as the timescales involved are far beyond current observation. Black holes can also exist in clusters, particularly in regions where many stars have formed and evolved. In such clusters, interactions between black holes can occur, leading to changes in their paths. Some of these interactions may result in mergers, while others may send black holes moving in new directions. The motion of black holes through space is governed by the same gravitational principles as all objects. They follow smooth trajectories, influenced by the mass and distribution of matter around them. Black holes do not emit signals that announce their presence, remaining quiet unless interacting with nearby material. This quiet nature makes them subtle components of the universe, present but not always visible. The study of black holes often relies on indirect observation, using the motion of stars and gas as indicators. By measuring these motions carefully, scientists can infer the presence and properties of black holes. In some cases, stars orbiting close to a black hole can be tracked over many years, revealing precise details. These observations provide strong evidence for the existence of supermassive black holes at galactic centers. Black holes can also influence the distribution of dark matter, shaping the structure of galaxies. Though dark matter itself is not directly observed, its gravitational effects can be measured. The interaction between black holes and dark matter remains an area of ongoing study. Black holes are consistent with the predictions of general relativity, which has been tested in many ways. These tests include the observation of gravitational waves and the behavior of light near massive objects. Each confirmation adds to the understanding of how gravity operates on both large and small scales. Black holes serve as natural laboratories for studying extreme conditions that cannot be recreated elsewhere. Despite their complexity, they follow simple underlying rules that remain steady and predictable. As these ideas continue to flow, they maintain a calm and even rhythm with no need to follow closely. Each fact settles quietly, leaving space for the next, forming a continuous stream that does not demand attention. The gentle pace remains unchanged, allowing the mind to rest while the quiet nature of black holes continues without interruption. Black holes can be compared by their mass, which determines many of their observable properties and the scale of their influence in space. A smaller black hole, formed from a single star, may have a mass several times greater than the Sun, yet remain compact in size. A supermassive black hole, by contrast, can hold the mass of millions or billions of stars, while still fitting within a region smaller than the orbit of some planets. The relationship between mass and radius remains simple, with larger mass leading to a proportionally larger event horizon. This relationship creates a sense of order, where even extreme objects follow clear patterns. Black holes can rotate, and this rotation affects the surrounding space-time in a smooth and continuous way. The rotation is described by angular momentum, which is conserved from the original star or material that formed the black hole. As a black hole spins, it drags space-time along with it, creating a region where motion cannot remain still. This region, known as the ergosphere, extends outside the event horizon and allows for subtle exchanges of energy. Objects entering this region must move in the direction of the black hole's rotation, carried gently by the flow of space-time. The structure of a rotating black hole is slightly more complex than a non-rotating one, but still follows predictable rules. Black holes can also carry electric charge, though in most natural situations, this charge is expected to be very small. The combination of mass, spin, and charge fully describes a black hole in classical physics. This simplicity is sometimes referred to as the idea that black holes have no additional features beyond these properties. Despite this simplicity, the effects they create in the surrounding environment can be varied and detailed. Black holes can interact with nearby stars, sometimes drawing matter from them in a slow and steady process. This transfer of matter can continue over long periods, forming a stable system where energy is gradually released. The light emitted from such systems often fluctuates gently, reflecting changes in the flow of material. These variations can be observed and studied, providing insight into the processes near the event horizon. Black holes can also exist in pairs, orbiting each other in a quiet and gradual dance. As they orbit, They emit gravitational waves that carry energy away, causing the pair to slowly move closer together. Over time, this leads to a merger, forming a single, larger black hole. The energy released during such a merger spreads outward as ripples in space-time, passing silently through the universe. These ripples can travel vast distances, eventually reaching detectors designed to measure their subtle effects. The detection of these waves confirms the presence of black holes and their interactions. Black holes can also be part of larger systems, such as galactic clusters, where many galaxies interact gravitationally. In these environments, supermassive black holes may influence not only their own galaxy, but also nearby structures. The motion of galaxies within clusters can be affected by the distribution of mass, including black holes. Black holes can remain stable over extremely long periods, maintaining their structure without change. Their stability comes from the balance of gravitational forces that define their existence. Even as they slowly gain or lose mass, their overall form remains consistent. The study of black holes often involves observing radiation across different wavelengths, from radio waves to X-rays. Each wavelength provides a different view of the processes occurring near the black hole. Radio waves can reveal large-scale structures like jets, while X-rays can show high-energy regions close to the event horizon. By combining these observations, a more complete picture can be formed. Black holes can also be simulated using computer models, allowing scientists to explore their behavior under various conditions. These simulations help visualize how matter moves and how light behaves near strong gravity. The results of these models often match observations, reinforcing the understanding of black hole physics. Black holes can influence the distribution of gas in galaxies, affecting how matter flows and accumulates. This influence can shape the overall structure of a galaxy, contributing to its long-term evolution. The balance between inflowing and outflowing material creates a steady state that can persist for long periods. Black holes can also produce winds, where particles are carried away from the accretion disk. These winds move outward at varying speeds, interacting with the surrounding medium. The interaction between these winds and the galaxy can regulate the supply of gas available for star formation. Black holes are often surrounded by a region of space where their gravitational influence is dominant. This region can extend far beyond the event horizon, affecting objects at considerable distances. Within this region, motion is guided primarily by the black hole's mass. Beyond this region, other gravitational influences begin to play a larger role. Black holes can be detected through the motion of stars that orbit them closely. These stars follow precise paths that can be measured over time. The speed and shape of these orbits provide information about the mass of the black hole. In some cases, stars move so quickly that their motion clearly indicates the presence of a very dense object. Black holes can also be part of systems where matter flows in a steady stream, creating a constant source of energy. This energy can be observed as a stable signal, allowing for long-term study. The consistency of these signals provides a calm and predictable pattern for observation. Black holes can exist quietly without interacting with nearby matter, making them nearly invisible. In such cases, their presence is inferred only through gravitational effects. This subtlety adds to the quiet nature of black holes, as they remain present without drawing attention. The universe contains many such objects, each existing in its own region, following the same gentle rules. As these facts continue, they maintain the same slow and even pace, allowing each idea to pass without effort. There is no need to follow closely, as the rhythm remains steady and unchanging. The quiet nature of black holes continues, forming a continuous background of calm and simple science. Black holes can be understood through the idea that mass shapes space-time, creating a smooth and continuous curve that guides the motion of everything nearby. This curvature becomes more noticeable as one moves closer, forming paths that gently bend inward without sharp edges. The concept remains consistent across different scales, from small stellar black holes to the largest supermassive ones. Each black hole, regardless of size, follows the same fundamental principles that describe its behavior. The energy near a black hole can take many forms, including radiation, motion, and heat within the surrounding material. These forms of energy move and change gradually, following the structure created by gravity. Black holes can also influence the direction of incoming matter, guiding it into circular or spiral paths. These paths form the accretion disk, where matter settles into a stable rotation before slowly moving inward. The disk itself can remain thin and flat, shaped by the balance between gravity and motion. Small disturbances in the disk may occur, but they tend to smooth out over time, maintaining a steady flow. Black holes can also affect the polarization of light, changing the direction in which light waves oscillate. This effect can be measured and used to study the environment close to the event horizon. The motion of particles near a black hole can reach very high speeds, approaching the speed of light. Despite these speeds, the motion remains smooth, following the curved paths defined by space-time. Black holes can also capture stray objects, such as asteroids or gas clouds, drawing them into orbit. Some of these objects may remain in stable paths for long periods, circling the black hole quietly. Others may gradually lose energy and drift inward, becoming part of the accretion disk. The process of capture and orbit remains gentle, unfolding over long timescales. Black holes can also exist in environments with very little surrounding matter, remaining almost completely inactive. In these cases, they do not produce noticeable radiation, blending into the background of space. Their presence is revealed only through the motion of nearby objects or subtle gravitational effects. Black holes can be described using coordinates that define their position and motion within a galaxy. These coordinates change slowly as the black hole moves under the influence of gravity. The motion itself is smooth and continuous, with no sudden changes. Black holes can also be influenced by the overall structure of the galaxy, including the distribution of stars and gas. This influence can cause gradual shifts in position over very long periods. The interaction between a black hole and its environment is often balanced, creating a stable system. Black holes can also affect the orbits of stars that pass nearby, slightly altering their paths. These changes are usually small, but can be measured with precise observations. The ability to measure such changes provides insight into the mass and location of black holes. Black holes can also act as anchors within galaxies, contributing to the stability of the central region. Their gravitational presence helps maintain the structure of stars and gas around them. This role is subtle and steady, without dramatic changes. Black holes can also be part of systems where multiple objects interact, creating complex but predictable motions. These systems can include stars, gas clouds, and other black holes, all moving under the influence of gravity. The resulting motion forms patterns that can be studied and understood. Black holes can also affect the flow of time for objects moving near them. Clocks closer to the black hole run more slowly compared to those farther away. Even in these quiet regions, particles continue to move and interact slowly. Magnetic fields exist throughout space, influencing the motion of charged particles. Cosmic rays are high-energy particles that travel through space, sometimes reaching Earth. Earth's atmosphere helps protect life by absorbing many of these energetic particles. Auroras occur when charged particles interact with Earth's magnetic field and atmosphere. These displays appear as soft lights near the polar regions, moving gently across the sky. The universe continues to expand in all directions, without a central point within it. This expansion is not in an empty space, but of space itself gradually increasing. On the largest scales, the universe appears uniform, with matter distributed in a similar way. Over time, gravity shapes this matter into clusters and structures. Galaxies can form clusters, which are groups bound together by gravity. These clusters can join into even larger structures called superclusters. Between these structures are vast voids where fewer galaxies are found. The large-scale structure of the universe resembles a web with strands and gaps. Each part of the structure evolves slowly over billions of years. The processes that shape the universe are steady and continuous, without haste. Stars vary in color depending on their surface temperature, with cooler stars appearing red and hotter stars appearing blue. The Sun is considered a medium-sized star, with a steady output of light and heat that has remained relatively stable for long periods. Sunlight is made of many wavelengths, including those visible to the human eye and others that are not directly seen. When sunlight passes through Earth's atmosphere, shorter wavelengths scatter more easily, giving the sky its soft blue appearance. At sunrise and sunset, the light travels through more of the atmosphere, allowing longer wavelengths to become more visible, creating warm tones. The vacuum of space does not carry sound, so even large cosmic events occur in silence. Temperature in space varies depending on exposure to radiation, with objects in direct sunlight becoming warm while shaded areas remain very cold. The International Space Station orbits Earth at an altitude where gravity is still present, but the station and its occupants are in continuous free fall. This creates the experience of weightlessness, where objects float gently without settling. Astronauts on long missions must exercise regularly to maintain muscle strength and bone density. Water behaves differently in microgravity, forming floating spheres rather than flowing downward. Fire also behaves differently in space, forming rounded shapes instead of rising flames. The boundary around a black hole, known as the event horizon, marks the point beyond which light cannot escape. Objects approaching this boundary appear to slow down when observed from a distance, due to gravitational effects on time. Inside a black hole, current physics cannot fully describe the conditions, leaving it as an area of ongoing study. Some galaxies contain active centers that emit strong radiation, powered by matter falling into central black holes. These regions can be observed across vast distances, appearing as bright points in the sky. Quasars are among the most luminous of these objects, shining steadily over time. Light can take billions of years to travel from distant quasars to Earth, carrying information from the early universe. The early universe was once much hotter and denser, gradually cooling as it expanded. As it cooled, particles combined to form simple atoms, primarily hydrogen and helium. These atoms later gathered under gravity to form the first stars and galaxies. Hydrogen remains the most abundant element in the universe, followed by helium. Heavier elements are less common and are formed through processes inside stars. The Hubble Space Telescope has captured detailed views of distant galaxies and nebulae. Newer telescopes continue to expand these observations, providing deeper views into space. Infrared telescopes can detect heat signatures from objects that are not visible in regular light. Radio telescopes detect signals from space at longer wavelengths, revealing different aspects of cosmic structures. The combination of multiple observation methods helps build a more complete picture of the universe. Meteorites are fragments of space objects that survive passage through Earth's atmosphere and reach the ground. Studying meteorites provides information about the early solar system. Some meteorites contain organic molecules, offering clues about the building blocks of life. The solar wind is a stream of charged particles flowing outward from the sun. Earth's magnetic field deflects much of this solar wind, helping to protect the atmosphere. During periods of high solar activity, the solar wind can intensify, affecting space weather. Space weather can influence satellite operations and communication systems. The heliosphere is a large region around the sun influenced by the solar wind. Beyond the heliosphere lies interstellar space, where the influence of the sun becomes weaker. The boundary between these regions is not sharp, but changes gradually. Gravity also influences the paths of light, causing it to curve near massive objects. This effect has been observed during solar eclipses, confirming predictions of relativity. Time and space are connected in a framework known as space-time, which can be shaped by mass and energy. Objects follow paths within space-time that appear as motion under the influence of gravity. The speed of light is constant in a vacuum, forming a fundamental limit for the transfer of information. No object with mass can reach or exceed this speed under current physical understanding. Distances in space are often measured in light years, representing how far light travels in 1 year. 1 light year is about 9.46 trillion kilometers, a distance that reflects the vast scale of the universe. Despite these distances, gravity continues to act across space, connecting objects over large scales. Galaxies sometimes interact and merge, slowly combining over millions of years. During such mergers, stars rarely collide directly because of the large distances between them. Instead, gravitational interactions reshape the structure of the galaxies. Over time, these processes can lead to the formation of larger galaxies. The Andromeda Galaxy is moving toward the Milky Way, with a slow approach that will take billions of years to unfold. This future interaction will gradually change the shape of both galaxies. On smaller scales, star clusters form groups of stars that share a common origin. Open clusters contain younger stars, while globular clusters contain older stars arranged in dense spheres. These clusters orbit within galaxies, maintaining their structure over long periods. Dust in space can block and scatter light, affecting how objects appear when observed. Infrared observations help see through this dust, revealing hidden regions of star formation. Some regions of space are rich in molecular clouds, where new stars are continuously forming. These clouds can collapse under gravity, leading to the creation of new stellar systems. The balance between gravity and internal pressure determines the stability of these clouds. Small fluctuations can grow over time, eventually leading to star formation. Brown dwarfs are objects that are too large to be planets, but too small to sustain stable fusion like stars. They emit faint heat and light, gradually cooling over time. The study of these objects helps bridge the understanding between planets and stars. White dwarfs, neutron stars, and black holes represent different possible endpoints of stellar evolution. Each type reflects the mass and conditions of the original star. Over long timescales, white dwarfs cool and fade, becoming less visible. Neutron stars can remain active through rotation and magnetic fields. Black holes continue to exist as stable regions defined by gravity. The universe contains background radiation from many sources, creating a steady environment of low-level energy. Even in the quietest regions, particles and fields interact in subtle ways. Space is filled with a network of forces and materials that operate without interruption. These processes occur slowly, often beyond the scale of immediate perception. The steady nature of these changes allows the universe to evolve gradually. There is no sudden shift in the overall structure, only continuous motion and transformation. Objects in orbit follow predictable paths shaped by gravity and initial motion. These paths can be calculated with high precision, allowing accurate predictions. Artificial satellites rely on these principles to maintain stable orbits around Earth. Deep space missions use gravitational assist to change speed and direction. By passing near planets, spacecraft can gain or lose energy without using additional fuel. This method allows exploration of distant regions with limited resources. The outer regions of the solar system remain less explored, with many objects still being studied. These distant bodies move slowly, reflecting the weaker influence of the Sun at large distances. The Oort cloud is a theoretical region that may contain many icy objects far beyond the Kuiper belt. It is thought to be the source of long-period comets that occasionally enter the inner solar system. These comets can take thousands or even millions of years to complete an orbit. Their paths are influenced by passing stars and gravitational interactions. The motion of stars within the galaxy also changes over time, though very gradually. Each star follows its own path while contributing to the overall structure. The universe continues in this steady way, with movement and change occurring quietly across vast distances. The surface of the Sun is not solid, but a layer of hot plasma that moves in slow, shifting patterns. Sunspots are cooler regions on the Sun's surface, appearing darker due to their lower temperature compared to surrounding areas. These sunspots follow cycles that last about 11 years, gradually increasing and decreasing in number. Solar flares are bursts of energy released from the sun's surface, sending radiation outward into space. These events can influence the space environment near Earth, though most effects are absorbed by the atmosphere. The sun's energy originates deep in its core, where pressure and temperature allow fusion to occur continuously. Energy produced in the core takes thousands of years to reach the surface, moving slowly through layers of dense material. Once it reaches the surface, it travels freely through space as light and heat. The solar system formed from a rotating cloud of gas and dust, gradually flattening into a disk. As material gathered, the sun formed at the center, while smaller bodies developed in orbit around it. Inner planets like Earth are rocky, while outer planets are composed largely of gas and ice. This difference is related to temperature variations during the formation of the solar system. Mercury, the closest planet to the sun, experiences large temperature changes between day and night. Venus has a thick atmosphere that traps heat, creating a stable but very warm surface environment. Earth's atmosphere contains a balance of gases that supports a wide range of conditions. Mars has a thin atmosphere, leading to cooler temperatures and less surface pressure. Some moons, such as Io, have active volcanoes driven by gravitational interactions. These interactions generate internal heat, leading to ongoing activity. Europa, another moon, is thought to have a subsurface ocean beneath its icy surface. This ocean remains liquid due to heat generated by tidal forces. Saturn's moon Enceladus releases plumes of water vapor into space from beneath its surface. These plumes suggest the presence of liquid water below the ice. The study of such environments helps expand understanding of where liquid water can exist. Water is a common molecule in the universe, found in various forms across different environments. Ice exists in cold regions, while vapor forms in warmer conditions. In space, water can be found in molecular clouds and on icy bodies. The presence of water contributes to the development of complex chemistry. Molecules in space can form through interactions between atoms and radiation. These processes occur slowly but continuously over time. Organic molecules have been detected in interstellar space, indicating that complex chemistry is widespread. These molecules can become part of forming planetary systems. As planets develop, they inherit materials from their surrounding environment. This includes gases, dust, and chemical compounds formed earlier in space. Gravity continues to shape planetary systems long after their formation. Orbits remain stable unless influenced by significant external forces. In some systems, planets may shift positions over time due to gravitational interactions. These movements can change the structure of the system. The study of these dynamics helps explain the variety of planetary systems observed. Binary star systems contain two stars orbiting a common center. These systems can have complex gravitational interactions affecting nearby objects. Some planets orbit binary stars, experiencing changing light conditions. Triple star systems also exist, though they are less common. The arrangement of stars influences how systems evolve over time. Stellar winds are streams of particles released from stars, similar to the solar wind. These winds can shape surrounding material, influencing the formation of new stars. Over time, stellar winds can clear out regions around stars, reducing available gas. This process contributes to the transition from star-forming regions to more stable environments. Interstellar dust grains are very small, often comparable in size to smoke particles. These grains can absorb and scatter light, affecting how distant objects appear. They also serve as surfaces where molecules can form. The distribution of dust helps trace the structure of galaxies. Observations at different wavelengths reveal different features of the same region. This layered view provides a more complete understanding of cosmic environments. Cosmic expansion continues at a steady pace, influencing the distances between galaxies. This expansion does not affect smaller structures like solar systems or galaxies directly. Instead, it becomes noticeable only across very large distances. The rate of expansion has been measured using various methods, including observations of distant supernovae. These measurements help refine understanding of the universe's history. Time since the beginning of expansion is used to estimate the age of a universe. As time progresses, stars continue to form, evolve, and eventually reach their endpoints. New generations of stars incorporate materials from earlier ones. This ongoing cycle contributes to the gradual enrichment of the universe with heavier elements. Galactic rotation curves provide evidence for the presence of unseen mass. This unseen mass, referred to as dark matter, influences how galaxies move. Without it, observed motions would not match predictions based on visible matter alone. Some nebulae are formed from the remains of exploded stars, spreading material into space. Supernovae occur when stars reach the end of their lives in powerful ways, releasing energy and matter. The elements created in stars are spread into space during these events, contributing to future star formation. Carbon, oxygen, and many other elements essential to life were formed in stars long ago. The Earth, and everything on it, is made from materials that once existed inside stars. Galaxies can take many shapes, including spiral, elliptical, and irregular forms. The Milky Way is a spiral galaxy, with arms that curve gently outward from its center. Stars within a galaxy orbit its center over very long periods of time. Our Sun takes about 225 million years to complete one orbit around the Milky Way. This slow movement happens without any noticeable change from day to day. The night sky appears steady, even though everything within it is in motion. Constellations are patterns formed by stars as seen from Earth, though the stars themselves are not physically connected. Over very long timescales, these patterns slowly change as stars move through space. Light from stars can be bent by gravity, a process known as gravitational lensing. This effect allows astronomers to observe distant objects that might otherwise be hidden. Time itself can be affected by gravity, passing more slowly in stronger gravitational fields. This effect has been measured and is part of the theory of relativity. Satellites in orbit around Earth must account for these small differences in time. Space probes have traveled beyond the planets, carrying instruments that continue to send data. The Voyager probes, launched in the 1970s, are now moving through interstellar space. They carry simple messages about Earth, encoded in a physical form. Interstellar space is the region between stars, filled with very thin gas and dust. Comets are made of ice, dust, and rock, and they develop glowing tails when they approach the sun. These tails form as heat causes materials to vaporize and stream away into space. Asteroids are rocky objects that orbit the sun, mostly found in a belt between Mars and Jupiter. Some asteroids occasionally cross Earth's orbit, though most remain at a safe distance. The sun contains more than 99% of the mass in the solar system, holding everything in orbit through gravity. Gravity is the force that shapes the motion of planets, stars, and galaxies, acting quietly across distances. Space itself is not completely empty, containing small amounts of gas, dust, and radiation. Between galaxies, there are vast regions where matter is spread very thinly. The observable universe includes all the light that has had time to reach us since the beginning of cosmic expansion. Because light travels at a finite speed, looking into space also means looking back in time. Distant galaxies appear as they were millions or billions of years ago, their light arriving only now. The cosmic microwave background is a faint glow that fills the universe, a remnant of its early state. This background radiation is very uniform, with slight variations that help shape the formation of galaxies. Dark matter is a form of matter that does not emit light, but can be detected through its gravitational effects. It plays a role in holding galaxies together, influencing how they move and form. Dark energy is thought to be responsible for the accelerating expansion of the universe. This expansion means that galaxies are gradually moving farther apart over time. The farther a galaxy is, the faster it appears to be moving away from us. This relationship is described by Hubble's law, which connects distance and velocity. Stars are often born in groups within large clouds called nebulae. These nebulae can glow softly when energized by nearby stars. There exists a region called the innermost stable circular orbit, where objects can maintain a steady path without falling inward. Inside this region, stable orbits are no longer possible, and matter begins to spiral toward the center. The size of this orbit depends on the mass and spin of the black hole. Faster spinning black holes allow stable orbits to exist closer to the event horizon. The rotation of a black hole can also affect the shape of the event horizon, making it slightly flattened at the poles. This rotation creates a dynamic structure where space-time itself is gently twisted. Black holes are often surrounded by halos of high-energy particles, forming a region of activity that extends beyond the disk. These particles can interact with magnetic fields, producing radiation across different wavelengths. The study of these emissions helps scientists understand the conditions near black holes. Black holes can exist quietly for long periods, with little material falling into them, making them difficult to detect. In such cases, their presence is inferred through the motion of nearby stars or gas clouds. The calm nature of these systems allows for steady observation over time. Some black holes may wander through space after being ejected from their original locations due to gravitational interactions. These isolated black holes would move silently through the galaxy, largely unnoticed. Detecting them requires observing subtle gravitational effects on nearby objects. Black holes can also act as gravitational lenses, magnifying distant stars and galaxies behind them. This effect can briefly brighten background objects as the black hole passes in front of them. Such events are rare, but provide valuable information about the distribution of black holes. The universe contains many black holes, each existing quietly within its own region of space. Black holes can have powerful magnetic fields generated by the motion of charged particles in the accretion disk. These magnetic fields can guide the formation of jets that extend far beyond the galaxy itself. Jets can travel at speeds close to the speed of light, carrying energy across vast distances in space. Despite their scale, these processes remain steady and continuous, unfolding without sudden shifts. Black holes can influence star formation in their galaxies by heating gas and limiting how it condenses. In some cases, this influence slows the formation of new stars, creating a balance within the galaxy. The interaction between black holes and galaxies forms a quiet relationship that evolves over long periods. Black holes also play a role in shaping the motion of stars near the centers of galaxies. Stars close to a supermassive black hole can orbit at very high speeds, following predictable paths shaped by gravity. These orbits can be measured to determine the mass of the black hole at the center. Astronomers use these observations to study the properties of black holes without directly seeing them. Black holes can also bend the path of radio waves, X-rays, and other forms of electromagnetic radiation. This bending allows scientists to observe effects that reveal the presence of strong gravity. The region just outside the event horizon can be described using general relativity, where space-time curves smoothly. This curvature determines how objects move, replacing the idea of force with the geometry of space and time. Objects in orbit around a black hole follow paths called geodesics, which represent the natural motion through curved space-time. These paths are smooth and continuous, shaped only by the structure of the gravitational field. The closer an object gets to the black hole, the more pronounced the curvature becomes. This results in orbits that can be tightly bound, looping close to the event horizon.